Your favorite topic and mine, sampling distributions. All right, ideas. What is a sampling distribution? What's an unbiased estimator? Talking about center, unusual features, variability, and shape for sampling distribution of means and proportions. Those are the ones we're going to work with. And doing probabilities, which that's like barely even a slide, even though it's the most important thing in here. A sampling distribution is all possible values of a statistic. I have good grammar, don't worry. Given a particular sample size. So like if there's a population of 1,000,000 people in it, and I sample 100, that's going to give me like one average, right? I'm finding all possible averages. That's what a sampling distribution is. A sampling distribution lets us examine how well a statistic estimates a parameter. Remember, statistic is a sample value, parameter is a population value. We want to estimate population values. So we want to know, does it estimate well? Does it consistently estimate well? So that's sampling distributions. An unbiased estimator is one whose sampling distribution is centered at the value of the parameter. It's called unbiased because it usually estimates the parameter well, so it's not centered somewhere else. We want estimators with low bias as well as low variability. Low bias means that we're typically guessing the right one. Low variability means we usually guess the right one, right? So we want to guess the parameter right with little variation. Cubs. So we usually only describe sampling distributions for means and proportions. The centers of these will always be the value of the parameter. So the mean of x bar should be equal to the real mean. The mean of p hat should be equal to the real proportion. Each of those have their own standard deviation formulas, which I wrote right there. If 10%, right? If the 10% conditions are met. The shape should be approximately normal if one of the conditions are met. So for proportions, remember we need large counts. For means, we either need the population to be normally distributed, or the sample size needs to be at least 30, or a graph of the sample data isn't like unreasonably skewed or has a bunch of outliers, right? We don't want outliers. If they're not met, if those conditions aren't met, the sampling distribution should look like the population's distribution. And we don't really do much regarding unusual features. Probabilities. If it's normal, should be able to use normal CTF. Great. Let's do some problems. There were 5,317 previously owned homes sold in a western city in the year 2000. The distribution of the sale prices of these homes was strongly right skewed, with a mean of 206,274 and a standard deviation of 37,881. If all possible simple random samples of size 100 are drawn from this population and the mean is computed for each of these samples, which of the following describes the sampling distribution of the sample mean? Okay, so the first thing each of these is talking about is shape. They said strongly right skewed. However, I said sample size is at least 30. So I say that it's normal. So it should be normal because the sample size is big enough. Now the mean should be the mean, but that didn't help me any. There is a standard deviation formula. If I take 37,881 and I divide it by the square root of n, that should be my standard deviation, A. Okay, the graphs of the sampling distributions, hello, thank you. The graphs of the sampling distributions 1 and 2 of the sample mean of the sample random variables for samples of 2 different sizes. Oh my God. Sampling distributions for 2 different sample sizes. That's basically all that says. Which of the following statements must be true about the sample sizes? So before I even look at the answer choices, I want to look at the actual graphs. Distribution 1 has significantly lower variability, right? It's not as spread out. So that means distribution 1 should have the larger sample size, which is B. Five estimators for a parameter are being evaluated. The true value of the parameter is 0. That seems important. True value of the parameter is 0. Simulations of 100 random samples of each of size n are drawn from the population. For each simulated sample, the 5 estimates are computed. The histograms below display the simulated sampling distributions for the 5 estimators. Which simulated sampling distribution is associated with the best estimator for this parameter? So remember, a good estimator is centered at the value of the parameter. The parameter is 0, so I want ones that are centered at 0. This one's not centered at 0. This one's not centered at 0. This one's not centered at 0. A or B? A would be a good estimator. B is better because it has lower variability. Big town fisheries. We recently stocked a new lake in a city park with 2,000 fish of various sizes. The distribution of the lengths of these fish is approximately normal. We're only going to do part A on this slide. I've got part B and C on other slides. Big town fishery claims that the mean length of the fish is 8 inches. If the claim is true, which of the following would be more likely? A random sample of 15 fish having a mean length that is greater than 10 inches, or a random sample of 50 fish having a mean greater than 10. Well, the real mean is 8. So as my sample size gets bigger, remember my my variability should be decreasing. So it should be less likely that I'd get a sample that far away, right? So here's what we're going to say. We are going to say it would be more likely with a sample size of 15. So with n equals 15. Because as sample size increases, variability from the mean decreases. I feel like we should mention the fact that 10 is above the mean. So we'll just say, and 10 inches, and 10 is greater than the mean. Something to that effect. That would do it. Suppose the standard deviation of the sampling distribution of the sample mean. Okay, so I've messed this problem up so many times because I've done it like over different years, and I always make the same mistake. Don't be me. This says the standard deviation of the sampling distribution of the sample mean. That is sigma sub x bar. They're not telling you sigma, they're telling you sigma sub x bar. So you should not divide that number by the square root of n. Don't be me. Anyway, suppose the standard deviation of the sampling distribution of the sample mean for random samples of size 50 is 0.3. So sigma sub x bar equals 0.3. If the mean length of the fish is 8 inches, so mu sub x bar is 8, use the normal distribution to compute the probability that a random sample of 50 fish will have a mean length less than 7.5 inches. So I'm just going to do this normal CDF. Lower. You can put negative infinity, but it probably makes logical sense to put 0 because you can't have a negative length for a fish. Upper is 7.5. The mean is going to be 8, and the standard deviation is 0.3. And if you go into your calculator, you get a number. Give me a moment. And that number is 0.0478. That's all. C, suppose the distribution of fish lengths in this lake was not normal. So the population is non-normal, but had the same mean and standard deviation. Would it still be appropriate to use the normal distribution to compute the probability in part B? Justify your answer. Well, it's not normal. Can I still use normal CDF? The population's not normal. The sampling distribution still is because, look, n is 50. If the sample size is greater than 30, then the sampling distribution is approximately normal. So yes, since the sample size is greater than, since n equals 50 is greater than 30, the sampling distribution is approximately normal. Boom. Summer Resort rents rowboats to customers but does not allow more than 4 people to a boat. Each boat is designed to hold no more than 800 pounds. Suppose the distribution of adult males who rent boats, including their clothes and gear, is normal with a mean of 190 pounds and standard deviation of 10 pounds. If the weight of individual passengers are independent, what is the probability that a group of 4 adult male passengers will exceed the acceptable weight limit of 800 pounds? Okay, so this one's a little weird because it doesn't really give you an average to consider, but it gives you enough information, right? So X bar for us is going to be 800 divided by 4, which is 200. I want to know the probability that the average person, average male for this, exceeds 200 pounds. Well, they said somewhere in here, yeah, there it is normal. So I'm just going to do normal CDF. Exceeds means that I need at least 200 per person. Upper, that'd be infinity, even though we can't have an infinitely large person. The mean of this distribution should be 190. The standard deviation should be equal to 10 divided by the square root of 4, right? Because we have to divide by the square root of n. This is different from big town fisheries. This is the population standard deviation. So I did have to divide by the square root of n this time. And if you give me a moment, you find that that probability is 0.023. Great news. We're done. Bye.